In this video we're going to do another direct proof involving cases, and we're going to do this one here. If n is odd, then n can be written in the form 4j minus 1 or 4j plus 1 for some integer j. So put your video on hold, try to write it out in symbols, and compare your answer to mine when you come back. Okay, so here it is written in symbols. For every integer n, if n is odd, then there exists an integer j such that either n is 4j minus 1 or n is 4j plus 1. So the first thing we should do before we actually try to prove it is that we should experiment with it to see if we really believe that it is true. You see, we have to prove it for every n, and so it's not enough for us to just test it out on a few n's. But nevertheless, in order to see if we believe it's true, we really ought to take a few specific n's and see if it's true. So let's do that next. We'll do that on some scrap paper. Okay, so our interest is in proving that we can write every odd integer either in the form 4j minus 1 or 4j plus 1. So let's see, can we do that, for example, with the odd integer 1? Well, 1 can be written as 4 times 0 plus 1, so that one works. That's 4 times 0 plus 1. What about 3? Well, 3 can be written as 4 minus 1. 4 times 1 minus 1, so that works. So it seems to be working. What about, I don't know, 21? How can we write 21 in this form? 21 can be written as what? 4 times 5 plus 1, so we can use this one. 4 times 5 plus 1. And what about 23? 23 can be written as 24 minus 1, 4 times 6 minus 1. Okay, so by doing this kind of experimentation, it doesn't prove anything, but it helps us to believe at least that it's true. In fact, if we had found that it didn't work for one of these, we would immediately say, well, the problem's not correct, we shouldn't go on. Now let's experiment some more. Let's write out the integers. And what we're going to do is we're going to look at the things of the form 4j, all the multiples of 4. Okay, so the multiples of 4 are here. I guess if we had written 0 in, maybe it's a good idea to write also 0. So the multiples of 4 are here, 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 and here. Now the 4j minus 1s, well, they appear 1 unit to the left. We're subtracting 1, so they'll be 1 unit to the left of these. So we're going to pick off 3, 7, 11, etc. And the 4j plus 1s, those are 1 unit those are 1 unit to the right of the 4j's. So those would be here, 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 and here. So you see, we seem to be generating all of the odd integers as either 4j minus 1 or 4j plus 1. Okay, so I guess we kind of believe that this thing should be true. So I think that's enough experimentation. Let's next see how we can actually prove the result. Let's begin by doing the routine part of writing up the proof. Since we've got the thing written out in symbols, and we know we're giving a direct proof, then we know what the first few sentences of the proof has to be. We start, because of this, by saying let n be an integer, and now, because it's direct, we're going to assume that the hypothesis is true by saying, suppose that n is odd. Now it's our task to prove that depending upon that n that we've just chosen, this statement is true. Now this statement is a little bit different from what we've worked with up until now, because it's what we call an existence statement. It asserts that there exists an integer j such that this happens. The way you prove something like that is true is that you explicitly explain how you're going to choose this j so that this happens. And that choice of j is somehow going to depend upon the integer n that you've just finished choosing. So let's do some calculations to see if we can figure out how to choose that integer j. So our assumption is that n is odd, and so we know that we can write n in the form 2k plus 1 for some integer k. And so now that we've got this k, it's going to be, what we're going to do is we're going to choose this j. We're going to choose this j somehow dependent upon this k over here. So everything is going to depend on that k. Well, we want n to be written either as 4j plus 1 or 4j minus 1. So evidently there are two cases, and so we have to view k in two different ways. So maybe the best idea is to either view k as even or odd. So let's first say, suppose k is even. That's our first case. Well, then that says that k is of the form 2 times I for some I. And if we now plug that in here for k, that then gives us that n is equal to 4i plus 1. And so that's exactly what we want. So we should then choose j equal to I in this case. And that will then give us that n is 4j plus 1 in this case. Okay, so now let's look at the second case. Second case, case 2, is the case where k is odd. If k is odd, then that means that I can represent k as 2i plus 1 for some I. And now what we do is we plug that in here and see how that represents n. So that's going to imply that n is, let's see, if you put 2i plus 1, so you get 4i plus 2 and 1 is 3, so you get 4i plus 3. Now we want to write it as 4j plus 1 or 4j minus 1. Since we've already got the 4j plus 1, my guess is that we won't be able to do that in this case, but rather we'll be able to get it as 4j minus 1. So why don't we just simply equate those two and solve for j in terms of I? This then implies that 4j equals 4i plus 4. And if you solve that for j, or if you divide by 4, you get j equals I plus 1. Okay, so that tells you how you should choose your j. You should choose j equal to I plus 1. And if you do that, and you plug in that value here, you'll discover that you get 4j minus 1. And so that you get what you want, this implies n equals 4j minus 1. Okay, so that's the kernel of the proof. We can build that into a correct proof. We've explained how to choose our j in each of the cases, dependent upon whether or not this I is even or odd. Okay, so now you go ahead and try to write up your proof, and I'll write up my proof, and we'll compare notes when you get back. Okay, here's the final version of the proof. I'm not going to go over it in detail with you, but I did want to point out a couple of things. I wanted to mention that when I introduce variables, I always include a quantifier. So you see here I introduced k. I didn't just put n equals 2k plus 1. I put there exists an integer k such that n is 2k plus 1. And when I introduced this I here, I didn't just say k equals 2i. It's a very common mistake that students make. That's where we're looking to see if you're going to do that correctly. I didn't just say k is 2i. I said there exists an integer I such that k is 2i. When I introduced the j, I didn't need to make a quantifier because I'm defining it to be something that I've already defined properly. Okay? So I mention that because on my scrap work here, I did everything very roughly and I didn't do things carefully. I just was trying to get the idea of the proof. But when you finally write everything up, everything has to be done perfectly.